Simplest form of a radical. A radical with index n is in simplest form if the radicand has no perfect nth powers, blah, 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 blah. So let's just define what these things are. So let's say you have this. Say you have that. The whole thing is called a radical. The y underneath here is called the radicand. What's underneath it is called the radicand. And then hopefully you all remember what the x is called from yesterday. The index. That's called the index. Okay? So if you're going to the simplest form of a radical, something that has a square root in it, or a third root or fourth root, you cannot have any of these little square root thingies or root signs in the denominator. You have to rationalize it, which we did at some point with square roots. And so we're going to get to that. Like radicals are radical expressions with the same index and radicand. So we'll look at those later. Okay, so here we go. Let's practice this. Use the properties of rational exponents to simplify the expression. So if you look at page 420, which you may or may not, but I'm going to show it to you anyway. May or may not need to. And you just say, just teach it to us. But then when you're doing your homework, if you're not sure, there's all these properties here that might help you if you need them. It's basically properties of rational exponents. But here we go. So look what you get to do here. When you're multiplying powers with the same base, what do you do to the exponent? Oh, and look, they're fractions, so you get to add fractions. Okay? Same base. So that means I have to add the fractions. And if you can't see, you can always move forward. All right, so they're not quite in the same denominator yet, so what would be the least common multiple for 6 and 8? 24, right on. So it would be 12 to the 3 over 24. Yes, plus, what do I multiply 6 by? 4, right? 20 over 24. And then you just add them together. 12 to the 23 over 24, that's as far as I can go. What do you multiply 6 by to get 24? It's okay. Everybody loves fractions.
Are we going to have to do this without a calculator on the side?
I don't know, you want to?
No. I mean,
I'm not that far yet.
I don't know if I can do it without it.
I could give you a times table if you'd like.
Well, I just want a calculator.
All right, so here we go. We're dividing with the same base. What do we do to the exponents when we divide with the same base? You subtract, but you say, but wait, there's no exponent here, but there really is. What number? 1. However, look at the denominator of this. It's 5, right? Yeah. So how could I write 1 as a fraction? 5, that would help me, yes. 5 over 5. Okay, so then I would have 10 to the 5 over 5 minus 2 over 5, which would give me what? 10 to the 3/5. And that's as far as I can go with that. Okay? All right, so here we are multiplying powers. They don't have the same base, but it doesn't matter. We have a power to a power. What do we do with that 3? You distribute it to the exponents only when it's multiply. You cannot do it when it's add or subtract in between there. Okay? So I'm going to have 5 to the 3 over 3 times 7 to the 3/4. Can I go any further? Can I make it prettier?
Yes.
What can I do? Yeah, 3 over 3 is just 1, right? So I wouldn't write that. Now, the only thing left is just to write it without that. You cannot go any further. You do not multiply 5 and 7 because that would not be following order of operations. Right? So this is as far as you can go. All right. This one here, we're dividing different bases. We still distribute that 5 to both of the exponents. We still distribute the 5 to both of the exponents. So we have 56, 5 over 4 to the 5 fourths, over 7 to the 5 fourths. Now, sort of, I think my preference would be to write it like this. Sometimes you just have to stop and look and say, what would be the best? They're raised to the same power, so I could actually write it like this. And then what happens? 56 divided by 7 is what? And so ultimately I would end up with this as the most simplified form. So sometimes just stop and look and say, wait a minute, what can I do here? You with me? Okay. All right, this one here. Multiply, yes.
Why don't you subtract the exponents?
Could. 5 fourths might be 0. It wouldn't work because we'd end up with 1, and we didn't start with 1, because anything raised to the 0 power is 1. Because if we subtracted this, we would have a 0 exponent, and anything raised to the 0 is 1. We didn't start with 1, so we can't leave an answer of 1, I guess.
Half to minus the exponent. I thought.
That's a good question on that one. I'm going to look into that for sure. But it's good thinking. I got to think about that one. All right, here, we still distribute. Let's distribute 2 to the negative 6 over 6 times 4 to the negative 6 over 6. Let's make that exponent prettier. 2 to the negative 1 times 4 to the negative 1. I don't want negative exponents in my simplification. That's not how you leave an answer when you're told to simplify. So how can I rewrite 2 to the negative 1 without a negative exponent? 1 over 2 times what? 1 over 4. That's rewriting this like this and rewriting this like that. Was from last chapter. Yes. I distributed negative 1/6 times 6. You got it? Okay. So there we go. There's that. Not so bad, huh? You know, I gotta say, I'm pretty What? Yeah, they're like, yeah. Hey, the ratio of the magnitudes. Let's keep going here. Okay, look at all these words, but this is like the easiest problem. It's not that scary. The ratio of the magnitudes of 2 earthquakes with magnitudes M1 and M2 as measured on the Richter scale is given by the equation. When they give you this, you got it made. Okay? The table gives the magnitudes of some of the largest earthquakes that have occurred in the U.S. How many times stronger was the 1964 quake in Alaska than the 1812 quake in Missouri? When you want to know how many times stronger something is, does the bigger number go on top or the smaller number go on top? The bigger. Okay? So we need to put Alaska on top. R equals, we don't even need R. We just need to do this. We just need to divide. We need to look at the magnitude of Alaska, which was what? In 1964 was 9.2. We're putting the M, this is the M1. And dividing it by, which one was it again? 1812, 7.9, 10 to the 7.9. This is M2. And then you whip out your calculator and you do the math. Yes, you can subtract. It's 10 to the 1.3. And then you can do that on your calculator. Is approximately, you get this really long number, 2, 3, or whatever it is, 6, 2, 3, whatever, blah, blah, blah. So you would say approximately 20 times stronger. See, not that scary, even though there's a lot of words. Okay, there's a lot of examples in this section. Turn it over.
It's bit 2.
All right, so this is something you're going to be practicing in your homework. This is one category on the front here. Then you're going to be doing stuff like this. Use properties of radicals to simplify the expression. All right, so let's look at here. They're both cubed, correct? So I can write it like this. I can multiply 125 times 8. It may help me. Oh, and look, it's such a pretty number. Do you think 1,000 has a cubed root?
Oh, yes.
What is it? 10. Okay. Yes. You could also take the cube root of 125, which is 5 times 2. You could also do it that way. Either way, doesn't matter. Okay? So this one here, there is no fourth root of 27. There is no fourth root of 3. So if I multiply them together, what's the fourth root of 81? Does anybody know? Sometimes you say, how do I know this? Well, what's the square root of 81? 9. So maybe I take it down again. It's 3. Make sense? 3 times 3 times 3 times 3 equals 3. Okay. Let's see. I don't know about a fifth root of 96. I know there isn't a fifth root of 3. But I could write this like this, if you remember root rules. Then I could do 96 divided by 3. So a lot of it is just kind of looking at it and say, what's going to get me where I need to go? And it's 2. Equals 2. And if you don't know, at this point, you can go on the calculator, okay? But you need to be able to show me these steps. All right, this one here, what do you think the best thing to do would be? The same thing. Cube root of 125 equals 5. So you're going to have to practice that kind of stuff. All right, write the expression in simplest form. Here we go. This is where we have to think of factors of 104 that are perfect cubes. And you say, I don't know what perfect cubes are, but you can come up with a list. How can you come up with a list of perfect cubes? Same thing, you came up with a list of perfect squares. What's 2 cubed? 8. What's 3 cubed? Does anybody know? Okay, so if you're not sure, write a little list down here and say to yourself, are any of these factors of 104? I don't know. Go on the calculator if you don't know. Divide by 8. Divide by 27. See which one is the biggest one that goes into it, and it happens to be just 8. So this becomes 8 times 13. And then you can take the cube root of 8, which is what? 2 times the cube root of 13. Don't forget, that's a new little step you got to stick in there, okay? That little 3. All right, here we're dealing with fourths, but we also have a thingy in the bottom. Can't have that. So we have to rationalize, okay? But there's more than just that. So first thing I'm going to do is make a list of perfect fourths. 2 to the 4th is 16, and I may need this list. I may not. 81. 4 to the 4th is 64. I don't know. I might need that list. Here's the deal. To get rid of this denominator here, I want a perfect fourth in the bottom. I want a perfect fourth. So I think I can take 27 to 81. Yes.
Yeah.
What?
You did 4 to the 4.
I'm sorry. It's 256. I wrote it down wrong. Okay. So I want to get rid of this denominator. I want to make it a perfect fourth.
Please excuse this interruption.
So what I'm going to do is I want to make the denominator a perfect fifth. So a perfect fourth. I'm going to multiply 27 by 3. Watch why I do this. And I'm going to multiply by the fourth root of 3. Just stay with me. Don't go what yet. You'll see why. And this is what I end up with. The fourth root of 81, that's going to help me get rid of that root sign in the denominator. And in the numerator, it becomes the fourth root of 30. This is called rationalizing the denominator. I'm really just multiplying by 1, aren't I? Is it this one?
Is there a number? I can't read it.
The fourth root of 3 over the fourth root of 3. Isn't that just the number 1? So it's perfectly mathematically legal. But what it helps me do is get rid of the root in the denominator. Because 81 is a perfect fourth, or whatever you call it. Got it? Now we're not done. What's the fourth root of 81? 3. The fourth root of 81 is 3. I can't do anything with that numerator, but I have simplified it because I've gotten rid of the root in the denominator. So this is my final answer. Okay, let's do this again. So this is the fifth root of 3/4. The first thing I'm going to do is split it up and make it the fifth root of 3 divided by the fifth root of 4. I just split up that fraction. I know I'm going to need a list of some perfect fifths. 2 to the 5th is 32. 3 to the 5th is 243. Probably that's all I'm going to work with. You could keep going if you had to. I want this denominator to be a perfect fifth. Can I get 4 to one of these?
Yeah.
Which one? 32. So I'm going to multiply the top and the bottom by the fifth root of what number? 8. Because that'll get me to the fifth root of 32. So I'm going to multiply the top and bottom by the fifth root of 8, which is really just multiplying by the number 1. It's perfectly legal, but it helps me get rid of that radical in the denominator. I'm going to take it down here because I'm running out of room. So go down here, and it looks like this. The fifth root of 24 divided by the fifth root of 32. And what's the fifth root of 32? 2. Can I do anything with the 24? Nope. Can't do anything with the 24, but that becomes that. It's kind of not too bad once you get going with it. Jason, you got a question? 1 cube root of 3. Okay? All right, simplify the expression. Assume all variables are positive. So let's look at this. Here's what I'm going to do. I'm going to start by splitting this up and write the fourth root of 625 times the fourth root of z to the 12th. Does 625 have a fourth root? 5 times 5 times 5 times 5. It's 5. This is where I want you to stop and think for a second. What does z to the 12th mean? Z times Z times Z times Z, 12 times, right? So how many groups of 4 Z's are in those 12? 3, correct? So if you think of it like that, this actually, the fourth root of Z to the 12, I can do that and just say it's simply Z to the 3. 12 divided by 4. All you got to do is 12 divided by 4. Remember what this means, and I can write it out this time, but it will take way too long to do it all the time. But look, this means 1, 2, 3, 4. There's one group of 4, correct? 1, 2, 3, 4. There's a second group of 4. So, and then there's 1, 2, 3, 4. There's 12 z's, right? The fourth root, I have 3 of those, which is equal to z cubed. You have to look at it like that. Or, if you don't want to look at it like that, just say, can I divide 12 by 4? Yes, and it gives me z cubed. Okay. Let's keep going and do a couple more of these. All right. So here, I have to the 1/5. Do you remember from yesterday? 32 to the 1/5 is the same thing as taking the 5th root, correct? So I'm going to rewrite it as the 5th root of 32 for that one. And then I'm going to distribute those exponents. So it would be m to the 5/5 times n to the 6. Come on, it's just multiplying fractions. You can do it. What's the 5th root of 32? 2. 5/5 is just m to the 1 times n to the 6, and that's it. Okay, I'm not going to do this one, but I will do this one. Let's do this one. Just for the sake of time. Let's split this up. I have the 6th root of r to the 6, so I'm going to write it like this. Yes. Ladies and gentlemen, what's the square root of x squared? X. What's the cube root of x cubed?
X.
What's the 6th root of r to the 6?
R.
R. Okay.
R over X.
R over, there are 3 groups of 6 s's. So it'd be r over s cubed, 18 divided by 6. That's your answer for that one. Wow. Okay, and we do need to do these two. These are very much like what's above, so I'm not going to do those. But let's do this. Write the expression in simplest form. Assume all variables are positive. Break it down so the exponent is a multiple of a root. You'll see what I mean here in a second. All right, so I'm going to take, and I'm going to rewrite this cubed root. Does 6 have any factors that are perfect cubes? No, so that's going to stay the same. X to the 4th, I'm going to rewrite like this. X cubed times x. Why would I do that? Because I can take the cube root of x cubed. Yes. Okay. Y to the 9th, I'm going to rewrite as, I'm just going to leave it as y to the 9th, and I'll show you why. Z to the 14th, I'm going to look at multiples of 3, so I'm going to write it as z to the 12th times z squared. Why would I do that? Because I can simplify c to the 12th, because it's a multiple of 3. So now I'm going to rewrite this like this. I can't do anything with the 6th. I can take the cube root of that, and I'm going to pull it out. It's x. I can't take the cube root of that next x. That's got to stay there. What's the cube root of y to the 9th? 9 divided by 3, which is what? 3. So it's going to be y to the 3rd, pulled out. Cube root of z to the 12th, you just do 12 divided by 3 would be out here, what? Z to the 4th. That's gone. And I can't do anything with z squared. That's got to stay under there. That's your answer. All right, let's just do this one and we'll be done. All right, you have to rationalize this. You have to not have a root in the answer. You have to rationalize. So let's split it up by writing 7p to the 8th divided by the 7 root of q to the 5th. My goal is to get rid of this stuff. It's a 7th root, but I only have 5 here. Well, what can I multiply by to get this maybe to 7? You know? Yeah, to get this exponent to 7. Q to the 5th times q to the what? Squared. So if I multiply the top and bottom by the 7th root of q squared, that's really just multiplying by 1, so it's perfectly legitimate. but it's going to help me get rid of that radical in the bottom. So I know I got some junk up on top here, which I'm going to worry about later. I'm going to rewrite p to the 8th as p to the 7th times p times q squared, because I multiplied this together. Because I ultimately want to get rid of that. Because I can take the 7th root of that, okay? And then in the bottom, it's q to the 7th. Almost done. This big boy math. Okay, that's it. That was a long one. Okay, so you got 15 minutes. Practice. We're not going to do, these are very similar to these. Okay, those are very similar to those, so it's not that different.